Welcome to Shri Learning Academy. Let's simplify structure of operating system. When we talk about the structure of operating systems, we are really talking about how an operating system is internally organized. Think of it like the layout of a building. From the outside, a house looks simple. You enter, you switch on lights, you use water, and everything just works. But inside the walls, there is wiring, plumbing, and careful planning. In the same way, an operating system looks simple to a user. You click icons, open apps, save files, and shut down the system. Behind the scenes, the operating system has a structure that decides how all these actions are handled. Different structures were designed over time to solve different problems such as performance, security, simplicity, and flexibility. Let us start with monolithic systems, because historically, this was one of the earliest and most common structures. In a monolithic operating system, the entire operating system is essentially one big program running in kernel mode. All major services like process management, memory management, file systems, device drivers, and system calls are part of a single large kernel. Imagine a large workshop where all workers sit in one big room. Everyone can directly talk to everyone else. If one worker needs help, they can immediately ask another. This is similar to a monolithic system. Every part of the operating system can directly communicate with every other part. This makes the system fast because there is very little communication overhead. Classic examples of monolithic systems include early versions of Unix and even modern Linux to a large extent. When a user program makes a system call, such as reading a file, control directly enters the kernel, and the file system code can directly call the disk driver code without any barriers. The advantage of this approach is performance. Since everything is tightly connected, operations are quick. There is no need to send messages between separate modules. However, there is a downside. The kernel becomes very large and complex. A bug in one part of the kernel can crash the entire system. For example, if a faulty device driver misbehaves, it can bring down the whole operating system. Debugging and maintaining such a system is also difficult because everything is mixed together. To solve some of these problems, researchers explored layered systems. In a layered operating system, the OS is divided into several layers, where each layer has a specific responsibility. Each layer only communicates with the layer directly above it or below it. You can think of this like a multi-story building. The ground floor might handle hardware interactions. The next floor might handle memory management. Above that might be process management. And at the top might be user interfaces. If someone on the top floor needs something, the request goes down step by step. In a typical layered system, the bottom layer is the hardware. Above that is the kernel core, then system services, and finally user applications at the top. Each layer hides its internal details from the other layers. This makes the system easier to design, understand, and debug. An example helps here. Suppose an application wants to read a file. The request goes from the application layer to the file system layer. The file system layer then interacts with the memory management layer and the input-output layer. Finally, the hardware layer accesses the disk. Each layer does its job and passes the result upward. The big advantage of layered systems is clarity and modularity. If something goes wrong in one layer, it is easier to identify and fix. It also becomes easier to modify or replace a layer without changing the entire system. However, the drawback is performance. Every request has to pass through multiple layers, which adds overhead. Because of this, pure layered systems are less common in practice, though the idea of layering influences many modern designs. This brings us to microkernels, which take modularity even further. In a microkernel architecture, the kernel is kept as small as possible. Only the most essential services are included in the kernel, such as basic process management, minimal memory management, and inter-process communication. Everything else, like file systems, device drivers, and network services, runs outside the kernel in user mode as separate processes. These components communicate with the microkernel using message passing. Imagine a small control center that only handles the most critical decisions. All other departments operate independently and communicate with the control center when needed. This is the idea behind microkernels. A well-known example of a microkernel-based system is Minix, which was designed for educational purposes. Another example is QNX, which is used in embedded and real-time systems such as car infotainment systems. The main advantage of microkernels is reliability and security. Since most services run in user mode, a failure in one service does not crash the entire system. For example, if a device driver fails, it can be restarted without rebooting the system. This is a huge benefit for systems that require high availability. However, microkernels also have disadvantages. Communication between user-level services and the kernel involves message passing, which can be slower than direct function calls in a monolithic kernel. Early microkernel designs suffered from performance issues. Modern systems try to optimize this, but the trade-off still exists. Closely related to microkernels is the client-server model in operating systems. In this model, the operating system services are treated as servers and user processes act as clients. Clients request services and servers respond to those requests. This model fits naturally with microkernels. For example, the file system can be a server process. When a user application wants to read a file, it sends a request to the file server. The file server then communicates with the disk driver server to access the hardware. Think of a restaurant. You are the client. The kitchen staff are servers. You do not go into the kitchen yourself. You place an order, and the kitchen prepares the food and sends it back to you. This separation makes the system more organized and safer. The client-server model improves modularity and makes it easier to distribute services. In some systems, servers can even run on different machines, which connects this idea to distributed operating systems that you will study later. The downside, once again, is communication overhead. Sending messages between clients and servers takes time compared to direct function calls. Next, let us talk about virtual machines, which you will revisit in much more detail in later modules on virtualization and cloud systems. In the context of operating system structure, virtual machines introduce a very interesting idea. Instead of one operating system directly controlling the hardware, a virtual machine monitor, also called a hypervisor, sits between the hardware and multiple operating systems. Each operating system thinks it has full control of the hardware, but in reality, the hypervisor manages and shares the physical resources among them. Each operating system runs inside its own virtual machine. Imagine a large house divided into several apartments. Each family feels like they have their own private home, even though they are sharing the same building. The landlord manages electricity, water, and maintenance. In this analogy, the landlord is the hypervisor. Virtual machines are extremely useful for testing, security, and cloud computing. You can run different operating systems on the same physical machine without them interfering with each other. If one virtual machine crashes, others continue running. From a structural point of view, virtual machines add an extra layer between hardware and operating systems. This layer increases flexibility but also adds some overhead. Modern hardware support for virtualization has greatly reduced this overhead, making virtual machines very popular today. Finally, we come to exokernels, which represent a more experimental and radical approach. The idea behind exokernels is to remove as much abstraction as possible from the kernel. Instead of the kernel managing high-level resources, it simply provides secure access to hardware resources. In traditional operating systems, the kernel decides how memory is allocated, how files are managed, and how processes are scheduled. In an exokernel system, these decisions are pushed to user-level libraries. The kernel only ensures protection and isolation. Think of the kernel as a strict security guard who gives you access to raw resources but does not tell you how to use them. You decide how to manage memory or files based on your application's needs. The advantage of exokernels is flexibility and performance. Applications can implement customized resource management strategies that suit them best. For example, a database application can manage memory differently from a multimedia application. The downside is complexity. Application developers now have much more responsibility, which makes development harder. Because of this, exokernels are mostly used in research rather than mainstream systems. When you look at all these structures together, you can see that there is no single perfect design. Monolithic systems are fast but complex. Layered systems are clean but can be slower. Microkernels and client-server models improve reliability and security but introduce communication overhead. Virtual machines provide isolation and flexibility but add extra layers. Exokernels offer maximum control but at the cost of simplicity. Modern operating systems often combine ideas from multiple structures. For example, Linux is largely monolithic but supports loadable kernel modules, which add some modularity. Windows uses a hybrid approach with elements of microkernels and monolithic kernels. This blending allows designers to balance performance, security, and maintainability. As you move forward in this course, especially when you study kernel mode versus user mode, system calls, and virtualization, you will see how these structural decisions affect real operating systems in practice. Understanding these structures now will help you make sense of why operating systems behave the way they do and why certain design choices were made. That is it for this video. See you in the next one.